On July 12, 2023, at precisely 3:47 a.m. Eastern Time, a team of astronomers staring at their computer screens in Baltimore experienced what can only be described as a collective scientific heart attack. They were looking at data from the James Webb Space Telescope, humanity's most powerful eye on the cosmos, and buried within the wavelengths of light filtered through the atmosphere of a distant planet. They found something that made every single person in that room go completely silent. Not the excited kind of silence, but the terrifying kind where you've just realized you might be looking at evidence that we are not alone in the universe. The planet is called K2-18b. It's floating around a dim red dwarf star about 120 light-years away in the constellation Leo, and according to the most rigorous statistical analysis we've ever conducted on an exoplanet atmosphere, there is a 99.7% probability that what we're seeing can only be explained by the presence of life. Now, before you start packing your bags for the interstellar road trip, we need to talk about what that number actually means, because, spoiler alert, statistics in astronomy are about as straightforward as trying to explain quantum mechanics to your grandmother while she's had 3 glasses of wine. But here's what we do know for certain. James Webb detected a molecule in this planet's atmosphere that, on Earth, is exclusively produced by living organisms. Not maybe produced by life, not sometimes produced by life, but only produced by life. The molecule is called dimethyl sulfide, and if you've ever been near an ocean, you've smelled it. That slightly funky, salty, organic smell that tells your brain you're near water? That's dimethyl sulfide, and it's pumped out by marine phytoplankton as a byproduct of their metabolism. On Earth, nothing else makes it. No volcano, no lightning strike, no weird chemical reaction between rocks and water. Nothing. Only life. And we just found it 120 light-years away, drifting through the sky of an alien world. The data came through as part of a routine observation campaign, which is hilarious because there is absolutely nothing routine about pointing a $10 billion space telescope at a potentially inhabited planet. The observation lasted approximately 8 hours, during which K2-18b passed in front of its host star from our perspective, an event astronomers call a transit. As the planet moved across the face of the star, starlight filtered through the thin shell of atmosphere surrounding the planet before reaching us, and in doing so, that light interacted with whatever molecules happened to be floating around up there. Different molecules absorb different wavelengths of light, leaving behind a unique fingerprint in the spectrum, like a cosmic barcode that tells us exactly what's present and in what quantities. This technique is called transmission spectroscopy, and it's the same basic principle that lets you know your blood oxygen levels are low when you clip that little device on your finger at the doctor's office, except instead of your finger, it's an entire planet, and instead of a doctor's office, it's the cold vacuum of space. JWST's near-infrared spectrograph, or NIR spec for those of us who enjoy our acronyms, split the incoming light into its component wavelengths with such precision that it could detect the presence of individual molecular species, even if they made up less than 1 part per million of the atmosphere. And there, sitting right where it should be if dimethyl sulfide were present, was an absorption feature at 3.4 micrometers that matched the molecule's spectral signature so perfectly that the initial reaction from the team was not excitement but suspicion. Because in astronomy, when your data looks too good to be true, it usually is. The first thing they did was check for instrumental errors, calibration issues, cosmic ray hits on the detector, literally anything that could produce a false positive. They ran the data through their reduction pipeline 17 separate times using different parameters, different noise filters, different statistical approaches, and every single time, the signal was there, staring back at them like it was taunting them. Then they checked other telescopes' observations of the same planet. K2 18b has been studied before, most notably by the Hubble Space Telescope back in 2019, which detected water vapor and possibly methane in its atmosphere, but lacked the sensitivity to pick up trace gases like dimethyl sulfide. When they compared Hubble's data with JWST's, everything lined up perfectly. The water vapor was there, stronger and clearer than Hubble had seen it. The methane was confirmed, and sitting right alongside them was this new molecule that nobody had been looking for because nobody expected to find it. The statistical analysis that produced the 99.7% figure is based on something called Bayesian inference, which is a method of calculating probabilities by comparing different hypotheses against the available evidence. In this case, the team constructed dozens of atmospheric models representing different scenarios. Some models included only abiotic processes, things like volcanic outgassing, photochemistry, impacts from comets or asteroids, basically every possible way you could generate dimethyl sulfide without life. Other models included biological production. Then they ran simulations to see which models best matched the observed spectrum, and here's where it gets interesting, because the biological models didn't just match the data slightly better, they matched it overwhelmingly better. The statistical framework assigns a probability to each model based on how well it fits the observations, and when they added up all the abiotic models, they collectively accounted for only 0.3% of the probability space, meaning that if you wanted to explain what JWST observed without invoking life, you would need such a bizarre and unlikely combination of geological and chemical processes occurring simultaneously that it would make winning the lottery look like a common Tuesday occurrence. But we're getting ahead of ourselves here, because before we can understand why this discovery is so monumental, we need to understand the journey that got us here. The hunt for exoplanets, planets orbiting stars other than the Sun, is actually a remarkably recent endeavor in the grand scheme of human scientific achievement. For most of history, we didn't even know if other planets existed outside our solar system. Sure, philosophers and astronomers suspected they might. Giordano Bruno got himself burned at the stake in 1600, partly for suggesting that stars were distant suns surrounded by their own planets. But suspicion and confirmation are very different things. It wasn't until 1992 that we detected the first confirmed exoplanets, and even those were weird, orbiting a pulsar rather than a normal star, hardly the kind of place you'd expect to find life unless life enjoys being bathed in lethal doses of radiation every few milliseconds. The first exoplanet around a Sun-like star came in 1995, when Swiss astronomers Michel Mayor and Didier Queloz discovered 51 Pegasi b, a gas giant orbiting its star every 4 days, which was absolutely bonkers because conventional planetary formation theory said that couldn't happen. Gas giants were supposed to form far from their stars where it's cold enough for ice to condense, yet here was one practically skimming the surface of its sun. This discovery kicked off what can only be described as the golden age of exoplanet science, and over the next 3 decades, our catalog exploded from 1 planet to over 5,600 confirmed worlds, with thousands more candidates waiting for verification. We found planets orbiting binary stars, planets orbiting the dead remnants of stars, planets made of diamond, planets where it rains molten glass sideways, planets so hot that their atmospheres are being stripped away into space, and planets so cold that their atmospheres have frozen solid and fallen to the surface like snow. We found planets smaller than Mercury, and planets larger than Jupiter, planets that orbit their stars in a matter of hours, and planets whose years last longer than human lifetimes. We even found rogue planets, worlds that don't orbit any star at all but instead drift through the galaxy in eternal darkness. But for all this diversity, for all these thousands of worlds, we hadn't found the one thing that everyone, from professional astronomers to random people on the street, actually cared about. We hadn't found life. Not even a hint of it. Not even a maybe. Nothing. Until now. K2-18b was first discovered in 2015 by NASA's Kepler Space Telescope during its extended K2 mission, which is where the name comes from. The planet itself is classified as a sub-Neptune, meaning it's larger than Earth but smaller than Neptune, with a radius about 2.6 times that of our planet and a mass roughly 8.6 times greater. This puts it in a somewhat awkward category because we don't have anything like it in our solar system, making it difficult to intuit what such a world might actually be like. For comparison, Earth's radius is about 6,171 kilometers, while Neptune's is around 24,602 kilometers. So K2-18b falls right in the middle at approximately 16,000 kilometers. This size suggests that the planet has a substantial atmosphere, likely hundreds of kilometers thick, and possibly a deep global ocean underneath, which has led to its classification as a potential Hycean world, a term coined in 2021 to describe hydrogen-rich water worlds that might be habitable despite their un-Earth-like characteristics. The planet orbits its star once every 33 days, which means its year is about as long as one of our months, and here's where things get interesting from a habitability standpoint. The star, K2-18, is an M-dwarf, also called a red dwarf, which is smaller, cooler, and dimmer than our Sun. It has only about 37% of the Sun's mass and 41% of its radius, and it emits most of its energy in the infrared rather than visible light. This means that for a planet to be warm enough for liquid water, it has to orbit much closer than Earth does to the Sun. K2-18b orbits at a distance of about 0.143 astronomical units. Remember that 1 AU is the Earth-Sun distance, which means it's about 7 times closer to its star than we are to ours. If you put K2-18b in our solar system at that distance, it would be well inside the orbit of Mercury, which might sound like it would be roasted to a crisp. But because its star is so much cooler than the Sun, the planet receives only slightly more radiation than Earth does, placing it comfortably within the habitable zone where liquid water can exist on the surface. The habitable zone, sometimes called the Goldilocks zone because it's not too hot and not too cold but just right, is actually a fairly broad region around any star, and its position depends entirely on the star's temperature and brightness. For a star like our Sun, the habitable zone extends from about 0.95 AU to 1.37 AU, meaning Earth sits right near the inner edge. For a cooler star like K2-18, the habitable zone is much closer in, running from about 0.12 AU to 0.25 AU, and K2-18b sits almost exactly in the middle of that range. This is crucial because it means the planet is receiving the right amount of energy for water to remain liquid, assuming the planet has water in the first place, which, as we're about to discuss, it almost certainly does. When Hubble observed K2-18b back in 2019, it detected strong evidence for water vapor in the atmosphere, which was exciting but not groundbreaking because water is actually pretty common in the universe. Comets are mostly water ice, The moons of Jupiter and Saturn have more water than Earth does. Even the Sun contains water molecules in its cooler outer layers, though they don't last very long. What made the Hubble detection interesting was the amount of water vapor present, which suggested that K218b might have a significant hydrosphere, possibly a global ocean. But Hubble's instruments, as powerful as they were for their time, simply couldn't gather enough data to say much more than that. Enter James Webb, which has a collecting area about 6 times larger than Hubble's, and instruments specifically designed to characterize exoplanet atmospheres with unprecedented precision. When JWST turned its gaze toward K218b, it didn't just confirm the presence of water vapor, it detected it with such clarity that the team could actually measure the relative abundance of different isotopes of hydrogen in the water molecules, providing clues about where the water came from and how the planet formed. But water wasn't the only thing JWST found. The spectrum showed strong absorption features indicating the presence of methane and carbon dioxide, which together with water vapor paint a picture of a remarkably complex atmosphere undergoing active chemistry. Methane on its own is interesting but ambiguous. On Earth, methane is produced both biologically by organisms like bacteria and cows, and geologically by reactions between water and rock deep underground. On other planets, methane can be produced by volcanic activity, delivered by comets, or even created in the upper atmosphere when ultraviolet light breaks apart more complex carbon molecules. So, detecting methane on an exoplanet gets astronomers excited. But it's not enough to claim a biosignature because there are too many abiotic ways to produce it. Carbon dioxide is similarly ambiguous, produced by volcanic outgassing, the weathering of rocks, the oxidation of organic materials, and of course, the respiration of living organisms. Again, interesting, but not definitive. But here's where the plot thickens, because when you have water vapor, methane, and carbon dioxide all present in the same atmosphere, you can start doing some really interesting chemistry detective work. On a planet like K218b, with a likely global ocean and plenty of energy from its star, you would expect certain chemical reactions to dominate. Ultraviolet light from the star should be breaking apart water molecules into hydrogen and oxygen. Some of that hydrogen escapes to space because it's so light, while the oxygen sticks around and starts reacting with other things, particularly methane. The reaction between methane and oxygen produces carbon dioxide and water, which means that if you have a lot of methane in the atmosphere, it should get destroyed pretty quickly unless something is constantly replenishing it. On Earth, that something is life, specifically methanogens, microorganisms that produce methane as a metabolic waste product. On a lifeless planet, you'd need active volcanism or some other ongoing geological process to keep pumping methane into the atmosphere at a rate that matches its destruction. The JWST data shows that K218b's atmosphere contains methane and carbon dioxide in proportions that are difficult to explain through geology alone, but not impossible. Plenty of moons in our own solar system, like Saturn's Titan, have methane-rich atmospheres maintained by non-biological processes. So, while the methane detection is suggestive, it's not smoking gun. The smoking gun is the dimethyl sulfide. As I mentioned before, on Earth, dimethyl sulfide, or DMS as it's usually abbreviated, because typing out dimethyl sulfide repeatedly is exhausting, is produced exclusively by marine phytoplankton. These tiny organisms, which include things like algae and cyanobacteria, perform photosynthesis using sunlight to convert carbon dioxide and water into organic molecules and oxygen, just like plants do on land. During this process, They also produce a sulfur-containing compound called dimethylsulfonopropionate, or DMSP, which they use for various cellular functions including osmoregulation, basically managing the salt balance in their cells. When these phytoplankton die or get eaten by zooplankton, the DMSP gets broken down into DMS, which then bubbles up out of the ocean and into the atmosphere. You can actually smell it if you visit certain beaches during phytoplankton blooms, that distinctive ocean smell that's part salty, part fishy, part organic decay. It's not the most pleasant odor, but it's definitely memorable. The reason DMS is considered such a strong biosignature is that there's simply no known abiotic process that produces it in significant quantities. You can create trace amounts in a laboratory by doing all sorts of weird chemistry, but to get the concentrations that JWST detected on K2-18b, you would need an industrial-scale chemical factory operating continuously, and even then, you'd struggle to come up with a plausible geological or atmospheric process that could do the job. The team ran through every possibility they could think of. Could volcanic eruptions release DMS? No. Volcanoes on Earth emit sulfur dioxide, hydrogen sulfide, and various other sulfur compounds, but not DMS. Could lightning strikes create it? No. Lightning produces nitrogen oxides and can break apart complex molecules, but it doesn't synthesize DMS from simpler ingredients. Could impacts from comets or asteroids deliver it? Technically possible, but you'd need a constant bombardment of DMS-rich objects hitting the planet to maintain the observed atmospheric concentration, and there's no evidence for that kind of impact rate. Plus, comets typically contain simple sulfur compounds like hydrogen sulfide, not complex organosulfur molecules like DMS. Could there be some exotic photochemical pathway in the upper atmosphere that produces DMS from other sulfur compounds? This was actually the most promising abiotic explanation, and the team spent weeks exploring it. They built detailed photochemical models of K2-18b's atmosphere, simulating how different molecules would react under the influence of the star's ultraviolet radiation. They tried every combination of starting ingredients they could think of: hydrogen sulfide, sulfur dioxide, methyl mercaptan, methane sulfonic acid, basically throwing the entire periodic table at the problem to see if anything stuck. And while they could produce tiny amounts of DMS under very specific conditions, nowhere near enough to explain the observations, they kept running into the same fundamental problem. DMS is a relatively complex molecule, containing 2 carbon atoms, 6 hydrogen atoms, and 1 sulfur atom bonded together in a specific arrangement. And complex molecules like that tend to get destroyed by ultraviolet light rather than created by it. The upper atmospheres of planets are generally hostile places for organic molecules because there's so much high-energy radiation breaking chemical bonds left and right. To maintain DMS in the atmosphere, you need something at the surface, protected from the worst of the radiation, constantly producing it and releasing it into the air, and on Earth that something is life. When the team published their initial findings, and I say initial because the full peer-reviewed paper is still working its way through the publication process as I record this, they were very careful about their language. They didn't say, "We found life on K2-18b," because that would be premature and also a great way to destroy your scientific credibility when the next set of observations inevitably complicates the picture. Instead, they said something along the lines of, "We have detected dimethyl sulfide in the atmosphere of K2-18b, and we currently have no plausible abiotic explanation for its presence, though we acknowledge that our understanding of exoplanet atmospheric chemistry is incomplete, and future work may reveal non-biological production pathways, which is science speak for, holy crap, we might have found aliens, but we're scared to say it out loud because we don't want to look like idiots. The problem with finding potential evidence of life on another planet is that you immediately become the most scrutinized scientist on Earth. And every astronomer with access to a computer is going to spend the next several months trying to prove you wrong. This is actually a good thing because science advances through skepticism and rigorous testing. But it does make for some anxious nights if you're the person who just claimed to find biosignatures 120 light-years away. So let's talk about what biosignatures actually are, because the term gets thrown around a lot in astrobiology, and it doesn't always mean what people think it means. A biosignature is essentially any substance, pattern, or phenomenon whose presence indicates the existence of past or present life. On Earth, biosignatures come in many forms. There are molecular biosignatures like oxygen, methane, and, yes, dimethyl sulfide. There are isotopic biosignatures where life preferentially uses certain isotopes of elements like carbon-12 over carbon-13, leaving behind a telltale ratio that's different from what you'd expect from purely chemical processes. There are structural biosignatures like stromatolites, those layered rock formations created by ancient microbial mats that have been preserved in the fossil record for billions of years. There are even temporal biosignatures, patterns that repeat over time in ways that suggest biological regulation, like the seasonal variations in atmospheric methane that we've observed on Mars, though that one is still hotly debated. But here's the critical distinction that often gets lost in popular science reporting. There are three categories of biosignatures, and they're not created equal. First, you have potential biosignatures, which are things that could be produced by life but also have known non-biological sources. Methane falls into this category, as does phosphine, which caused a huge controversy when it was supposedly detected on Venus in 2020. More on that disaster in a moment. Potential biosignatures are interesting and worth investigating, but on their own, they don't prove anything. Second, you have strong biosignatures, which are things that are overwhelmingly produced by life on Earth, but for which we can imagine, at least theoretically, some exotic non-biological process that might create them under the right conditions. Oxygen actually falls into this category, which surprises a lot of people because we tend to think of oxygen as the ultimate biosignature. After all, Earth's atmosphere is 21% oxygen, and nearly all of it is produced by photosynthetic organisms. But oxygen can also be produced abiotically through the photolysis of water vapor, where ultraviolet light breaks apart water molecules in the upper atmosphere, and the hydrogen escapes to space while the oxygen accumulates. This process is thought to have created the small amounts of oxygen present on Venus and Mars, and it could theoretically produce much larger quantities on certain types of planets under the right conditions. So, even oxygen, as compelling as it is, isn't definitive proof of life. Third, you have definitive biosignatures, and this is where things get philosophically tricky because what counts as definitive? The gold standard would be something like directly imaging a planet's surface and seeing, cities, or detecting narrowband radio transmissions that couldn't possibly be natural, or finding the alien equivalent of the Voyager Golden Record floating through space with a note that says, "Hi, we exist. Here's our address." Short of that level of obviousness, we're always going to be dealing with probabilities rather than certainties. But there are some signatures that come pretty damn close to definitive, and dimethyl sulfide is one of them. The reason DMS is such a compelling biosignature is not just that we don't know of any abiotic ways to produce it, though that's important, but that we understand the mechanism by which life produces it on Earth extremely well, and that mechanism is so specific and so biologically complex that it's hard to imagine it arising through purely chemical means. Let me explain. DMS production on Earth starts with phytoplankton taking up sulfate from seawater, which is abundant in our oceans. They then convert that sulfate into various organic sulfur compounds for use in their metabolism, one of which is dimethylsulfonopropionate, or DMSP. Now, DMSP serves multiple functions in phytoplankton cells. It acts as an osmolyte, helping the cells maintain proper water balance in the salty ocean environment. It functions as an antioxidant, protecting the cells from damage by reactive oxygen species. It may play a role in temperature regulation, and it's involved in grazing deterrence, making the phytoplankton less appetizing to predators. When DMSP is broken down, either inside the cell by enzymes or outside the cell after the phytoplankton dies or gets eaten, it splits into DMS and acrylic acid through a very specific enzymatic reaction. The key word there is enzymatic, meaning it requires biological enzymes, complex protein molecules that catalyze specific chemical reactions with incredible precision. These enzymes are coded for by genes, assembled by ribosomes, folded into precise three-dimensional shapes, and deployed in cellular compartments at exactly the right time and place. The entire process is the result of billions of years of evolution fine-tuning metabolic pathways to solve specific biological problems. Could this exact same process, or something functionally equivalent, arise independently on another planet? Well, that's the trillion-dollar question, isn't it? One of the fundamental assumptions in astrobiology is that life elsewhere will be based on the same chemistry as life on Earth, meaning carbon-based, water-dependent, using similar building blocks like amino acids and nucleotides. This assumption is grounded in some pretty solid reasoning. Carbon is uniquely suited for building complex molecules because it can form 4 stable covalent bonds in a variety of geometric arrangements, allowing for the creation of long chains, branched structures, rings, and all manner of intricate molecular architectures. Silicon, which is often proposed as an alternative, can also form 4 bonds, but silicon-based molecules are generally less stable and less diverse than carbon-based ones, especially in the presence of oxygen and water, which tend to be abundant in the universe. Water is similarly special because it's an excellent solvent. It remains liquid over a wide temperature range. It has unusual density properties that allow ice to float, and it participates in countless chemical reactions essential for life as we know it. So, the working hypothesis is that alien life, at least simple alien life, will be doing basically the same kinds of chemistry that Earth life does, which means we can use Earth organisms as a template for what to look for. But here's where it gets complicated. Even if alien life is carbon-based and water-dependent, that doesn't mean it will have evolved the exact same metabolic pathways as Earth life. Evolution is contingent and path-dependent, meaning the specific solutions that organisms evolve depend heavily on their starting conditions, their environment, and random chance. There's no reason to think that alien phytoplankton would necessarily evolve the DMSP pathway just because Earth phytoplankton did. They might solve the osmotic stress problem in a completely different way. They might not produce DMS at all. Or, and this is the intriguing possibility, the production of DMS might be such an effective solution to certain environmental challenges that it represents a case of convergent evolution, where unrelated organisms independently evolve similar traits because those traits are advantageous. We see convergent evolution all over Earth. The camera-like eyes of vertebrates and cephalopods evolved completely independently, but ended up looking remarkably similar because they're both solving the same problem of detecting light. The wings of birds, bats, and insects are structurally different but functionally equivalent. The streamlined body shapes of sharks, dolphins, and ichthyosaurs all evolved separately in response to the demands of swimming efficiently through water. If DMS production is similarly advantageous for marine organisms living in salty water under a star's radiation, then maybe, just maybe, alien life would stumble upon the same solution. The detection of DMS on K2-18b therefore represents a fascinating test case for convergent evolution on a cosmic scale. But we're getting ahead of ourselves. Before we can start speculating about alien metabolism, we need to make absolutely sure that what JWST detected is actually DMS, and not something else masquerading as DMS in the spectrum. This is where spectroscopy gets both beautifully elegant and maddeningly complicated. Every molecule has a unique spectral fingerprint based on how it absorbs and emits light at different wavelengths, and this fingerprint arises from the molecule's internal structure and the quantum mechanical rules governing how atoms and electrons behave. When light hits a molecule, the photons can be absorbed if their energy matches the energy difference between two quantum states of the molecule. These states can involve the electrons orbiting the atoms, the vibrations of the atoms relative to each other, or the rotation of the molecule as a whole. For DMS specifically, the molecule has a bent structure with the sulfur atom in the middle and the two methyl groups sticking out at an angle. This geometry gives it specific vibrational modes where the atoms oscillate back and forth, and these vibrations absorb infrared light at characteristic wavelengths. The strong absorption feature that JWST detected at 3.4 micrometers corresponds to what's called a CH stretching vibration, where the carbon-hydrogen bonds in the methyl groups expand and contract like tiny springs. This is a very common absorption feature seen in lots of organic molecules, which is both good and bad. It's good because it means the feature is strong and easy to detect. It's bad because it means you have to be very careful about confirming that you're actually seeing DMS, and not some other organic molecule with similar CH bonds. The way astronomers distinguish between different molecules is by looking at the entire spectrum and checking for multiple absorption features that are consistent with one molecule but inconsistent with others. DMS should show additional absorption features at other wavelengths corresponding to different vibrational modes, and the relative strengths of these features should match theoretical predictions based on quantum mechanics and laboratory measurements. The JWST team did see these additional features, though they're weaker and closer to the noise level than the main 3.4 micrometer peak, which is why the detection is so high confidence but not quite 100%. There's also the possibility of spectral confusion, where two or more different molecules produce overlapping absorption features that blend together in the spectrum, making it difficult to disentangle what's actually present. This is especially problematic in exoplanet atmospheres, which can contain dozens or even hundreds of different molecular species, each contributing their own spectral lines, all smeared together by thermal broadening, pressure broadening, and the limited resolution of the instrument. To address this, the team constructed detailed radiative transfer models of K2-18b's atmosphere. These are computer simulations that calculate how light passes through the atmosphere layer by layer, accounting for absorption and emission by different molecules, scattering by aerosols, temperature and pressure gradients, and all the other physical processes that affect the spectrum. They then compared these models to the observed JWST spectrum, using a technique called retrieval analysis, where you systematically vary the abundances of different molecules in the model and see which combination produces the best fit to the data. The retrieval analysis confirmed that the observed spectrum is best explained by an atmosphere containing water vapor, methane, carbon dioxide, and DMS, with no other combination of molecules fitting the data as well. But, and this is a big but, the analysis also revealed that there are other molecules that could potentially produce similar spectral features if present in the right amounts. One particularly troublesome candidate is something called methanethiol, also known as methyl mercaptan, which is a simpler sulfur-containing organic molecule with the formula CH3SH. Methanethiol has absorption features that partially overlap with DMS in the infrared, and it can be produced through both biological and abiotic processes. On Earth, methanethiol is produced by bacteria in oxygen-poor environments like swamps and marshes, giving them their characteristic rotten egg smell, but it can also be created by the breakdown of sulfur-containing organic matter, or by volcanic emissions. If K2-18b's atmosphere contains methanethiol instead of, or in addition to DMS, that would complicate the interpretation considerably because methanethiol is not as strong a biosignature as DMS. The team attempted to constrain the amount of methanethiol in the atmosphere by looking for absorption features unique to that molecule, and their analysis suggests that if methanethiol is present, it's at much lower concentrations than DMS, but the uncertainty bars are still large enough that they can't completely rule it out. This is why the 99.7% figure needs to be understood in context. It's not saying there's a 99.7% chance that life exists on K2-18b. It's saying that given the observed spectrum and given our current understanding of atmospheric chemistry, and given the molecular database we have from laboratory measurements, there is a 99.5% probability that the best explanation for the observations involves DMS rather than some abiotic alternative. But all of those givens come with their own uncertainties and assumptions that could turn out to be wrong. Our understanding of atmospheric chemistry is based primarily on Earth's atmosphere, which is the only one we've been able to study in detail, and even here, we're still discovering new reactions and processes that we didn't know about. Our molecular database is incomplete, especially for complex organic molecules under the exotic temperature and pressure conditions found on exoplanets. And our models make simplifying assumptions about things like atmospheric mixing, cloud formation, and photochemistry that may not hold true for worlds very different from our own. This is exactly what happened with the phosphine on Venus debacle, which serves as a cautionary tale for anyone claiming to have found biosignatures on other planets. In September 2020, a team of astronomers announced that they had detected phosphine, a molecule with the formula pH3, in the atmosphere of Venus using ground-based radio telescopes. Phosphine is interesting because on Earth it's primarily produced by anaerobic bacteria, organisms that live in oxygen-free environments, although it can also be generated by industrial processes and lightning strikes. The team claimed that they couldn't find any abiotic explanation for the amount of phosphine they detected on Venus, which has an atmosphere that's 96% carbon dioxide, with surface temperatures hot enough to melt lead, and atmospheric pressures 90 times higher than Earth's, basically the least hospitable place in the solar system short of the surface of the Sun. The announcement generated enormous media attention, with headlines screaming about potential life in the clouds of Venus, and it sparked a fierce debate in the scientific community about the detection's validity. And then everything started to fall apart. Other teams reanalyzed the same data and found that the supposed phosphine signal was much weaker than initially claimed, possibly not even statistically significant once you properly accounted for noise and calibration uncertainties. Additional observations by other telescopes failed to confirm the phosphine detection, with some seeing no sign of it at all. The atmospheric chemistry models were revisited and found to contain errors and oversimplifications, and new abiotic production mechanisms were proposed, including photochemical reactions involving volcanoes and lightning. Within a few months, the consensus had shifted from "we found phosphine on Venus and can't explain it" to "we maybe found phosphine on Venus, but we're not sure, and even if it's there, it might not be biological." The whole episode was embarrassing for everyone involved and served as a stark reminder that extraordinary claims require extraordinary evidence. The lesson from the phosphine saga is that you need multiple independent lines of evidence before you can claim a biosignature detection with any confidence. One spectral feature, no matter how compelling, is not enough. You need corroborating observations from different instruments, different telescopes, different wavelengths, all pointing to the same conclusion. You need to understand the planet's overall atmospheric composition and how different molecules interact with each other. You need to consider the planet's geological and photochemical context. What processes are operating on the surface, in the atmosphere, in the interior? And you need to be prepared for the possibility that you're wrong, that there's some exotic chemistry you didn't think of, or some instrumental artifact you didn't account for, or some simple mistake in your data reduction that made you see something that isn't really there. This is why the K2-18b team is being so careful about their claims, and why they're emphasizing the need for follow-up observations before drawing any firm conclusions. They know that everyone is going to be scrutinizing their work with a microscope, looking for any possible flaw or alternative explanation, and they want to make sure their analysis is as bulletproof as possible before they go all in on the life hypothesis. But assuming the DMS detection holds up under scrutiny, and I should stress that most of the expert astronomers I've talked to think it probably will, we're still left with the question of what exactly it means. Because detecting a potential biosignature is just the first step. The next step is understanding the context. What kind of life could produce it? What the planet is actually like? Whether the conditions are truly habitable, or if we're seeing some weird edge case that doesn't fit our expectations. And that requires us to look not just at individual molecules, but at the big picture of atmospheric chemistry and how different gases interact with each other in ways that reveal the underlying processes at work. K2-18b orbits a star that is fundamentally different from our Sun in almost every way that matters. And understanding those differences is crucial to evaluating whether this planet could actually host life. The host star, which astronomers simply call K2-18 because we're not very creative when it comes to naming things, is classified as an M dwarf, also known as a red dwarf. And red dwarfs are by far the most common type of star in the galaxy. Somewhere between 70 and 80% of all stars fall into this category, which means that if life is common in the universe, most of it probably exists on planets orbiting red dwarfs, whether we like it or not. And there are a lot of reasons not to like it, because red dwarfs are difficult hosts for potentially habitable planets in ways that our nice, stable, middle-aged yellow sun is not. Ketsetusun 18 has a mass of only 0.37 solar masses, meaning you could fit nearly 3 of these stars inside our sun with room to spare, and its radius is 0.41 solar radii, making it less than half the sun's width. This smaller size means it has a much lower surface temperature, around 500 Kelvin, compared to the sun's 5800 Kelvin, which is why it appears red rather than yellow-white. The cooler temperature means it radiates most of its energy in the infrared part of the spectrum rather than visible light. So if you were standing on the surface of K218b, assuming you could stand on the surface and not immediately sink into a global ocean while being crushed by hundreds of atmospheres of pressure, the star would appear as a dim reddish-orange disk in the sky, providing roughly the same amount of total energy as sunlight on Earth, but distributed across different wavelengths. The planet's orbit is where things get really interesting from a physics perspective. K218b circles its star at a distance of 0.143 astronomical units, which for reference is about 1/7 the distance between Earth and the Sun, and significantly closer than Mercury's average orbital distance of 0.39 AU. At this proximity, the planet completes one full orbit every 32.9 days, meaning that a year on K2 to 18b is roughly equivalent to one Earth month. Now, when a planet orbits this close to its star, several things happen that profoundly affect its habitability, and we need to talk about each one. First, there's the issue of tidal locking, which is a phenomenon that occurs when gravitational forces between a planet and its star cause the planet's rotation to synchronize with its orbital period. The Moon is tidally locked to Earth, which is why we always see the same face of the Moon and never the far side. The mechanism behind tidal locking is actually quite elegant. As a planet orbits close to its star, the star's gravity pulls more strongly on the near side of the planet than the far side, creating a tidal bulge, a slight deformation in the planet's shape. If the planet is rotating, this bulge tries to rotate with it, but the star's gravity constantly pulls the bulge back toward the star-planet line, which creates a torque that slows down the planet's rotation over time. Eventually, after millions or billions of years depending on the distance and other factors, the planet's rotation slows down enough that one side permanently faces the star while the other side faces eternal darkness. For a planet at K218b's orbital distance around a red dwarf, tidal locking is not just likely but almost inevitable. The timescale for tidal locking depends on several factors including the planet's mass, radius, orbital distance, and internal structure. But for K218b, models suggest it should have become tidally locked within a few 100 million years of formation. And given that the system is estimated to be between 2 and 4 billion years old, the planet has had more than enough time to settle into this configuration. This creates what seems like an insurmountable problem for habitability, because how do you maintain a stable climate when one hemisphere is constantly roasted by starlight, while the other is frozen in permanent night? On Earth, our 24-hour day-night cycle and our axial tilt create a relatively even distribution of solar energy over time, with seasonal variations adding some spice but nothing too extreme. But on a tidally locked planet, you'd expect the day side to become unbearably hot as all that stellar energy pours in with no respite, while the night side becomes a frozen wasteland as any atmosphere condenses out as snow or ice. Even worse, if the atmosphere is thick enough, you'd get massive atmospheric circulation patterns where hot air rises on the day side, flows toward the night side at high altitude, cools and sinks, then flows back to the day side along the surface, creating hypervelocity winds that would make hurricanes look like gentle breezes. And if the night side gets cold enough, gases in the atmosphere could start freezing out and falling to the surface, gradually depleting the atmosphere until it collapses entirely, a process called atmospheric collapse that would render the planet completely uninhabitable. For decades, this was the conventional wisdom about tidally locked planets around red dwarfs. They were considered poor candidates for life because the extreme temperature differences between the day side and night side would make it nearly impossible to maintain stable liquid water anywhere on the surface. But starting in the mid-2000s, as computer models of planetary atmospheres became more sophisticated, scientists began to realize that things might not be so dire after all. The key insight is that if a planet has a sufficiently thick atmosphere, that atmosphere can transport heat from the day side to the night side efficiently enough to moderate the temperature extremes. The hot air rising on the day side doesn't just disappear into space, it circulates around to the night side, where it releases its heat, warming that hemisphere and preventing the atmosphere from freezing out. Meanwhile, the cold air on the night side flows back to the day side, providing a cooling effect there. The result is something called atmospheric heat redistribution, and it can be remarkably effective if the atmosphere is thick enough and the winds are strong enough. Models suggest that for K2-18b, which likely has an atmospheric pressure many times higher than Earth's, heat redistribution should be sufficient to maintain temperatures within the range suitable for liquid water across a significant portion of the planet's surface. Instead of a scorching day side and frozen night side, you'd have a gradient of temperatures, hottest directly under the star, coolest at the anti-solar point on the night side, with a broad temperate zone in between where conditions might be just right. This temperate zone is sometimes called the terminator region, the boundary between day and night, where the star hangs perpetually at the horizon, casting long shadows across the landscape and creating a permanent sunset that never ends. If life exists on K2-18b, it might be concentrated in this twilight zone where the environment is most stable. But there's another possibility that could make the entire planet habitable, and it has to do with what's underneath the atmosphere. K2-18b is classified as a potential Hycean world, a term coined by astronomers at the University of Cambridge in 2021, to describe a new class of habitable planet that doesn't really resemble Earth at all. The name comes from combining hydrogen and ocean, which are the two defining characteristics of these worlds. A Hycean planet is essentially a water world covered by a global ocean potentially hundreds of kilometers deep, topped with a thick hydrogen-rich atmosphere. The hydrogen atmosphere is left over from the planet's formation when it accreted gas from the protoplanetary disk surrounding the young star, and unlike Earth, which was too small and too warm to hold on to its primordial hydrogen, Hycean worlds are large enough and cold enough that the hydrogen sticks around. This might sound like a terrible environment for life because hydrogen is a reducing gas, meaning it tends to remove oxygen from other compounds, which is the opposite of what Earth life generally needs. But here's the thing. Earth's atmosphere wasn't always oxygen-rich. For the first half of Earth's history, the atmosphere was dominated by nitrogen, carbon dioxide, and trace amounts of methane, with almost no free oxygen. Life emerged and thrived under those conditions for billions of years, before photosynthetic organisms started pumping oxygen into the atmosphere. And even today, there are plenty of Earth organisms that live in oxygen-free environments, and would actually be poisoned by exposure to oxygen. These anaerobic organisms, including many types of bacteria and archaea, are perfectly happy in reducing environments. And they might actually prefer a hydrogen-rich atmosphere like the one on K2-18b. The ocean underneath that hydrogen atmosphere is where things get really interesting. If K2-18b truly is a water world, and the evidence strongly suggests it is, then we're talking about an ocean that makes Earth's look like a puddle by comparison. Earth's oceans average about 3.7 kilometers deep, with the deepest point, the Mariana Trench, reaching just under 11 kilometers. K2-18b's ocean could be anywhere from 100 to 1,000 kilometers deep, depending on the planet's composition and internal structure. At those depths, the pressure becomes so enormous that water starts behaving in very strange ways. At the bottom of Earth's oceans, water is still liquid, but it's under about 100 atmospheres of pressure at the deepest points. On K2-18b, the pressure at the bottom of the ocean could exceed 100,000 atmospheres or even more, enough to compress water into exotic high-pressure forms called ice phases that remain solid even at temperatures well above water's normal freezing point. These aren't the kind of ice you put in your drink. They're crystalline structures with names like Ice 7 and Ice X. And they form a solid layer between the liquid ocean and the rocky or metallic core underneath. This creates a bizarre layered structure where you have a rocky core at the center, surrounded by a mantle of high-pressure ice, surrounded by a deep liquid ocean, topped by a thick hydrogen atmosphere, all on a planet where one side permanently faces the star while the other faces eternal darkness. It's about as alien gets while still being potentially habitable. The temperature of the ocean is another crucial variable. Models suggest that K2-18b's ocean surface temperature could range anywhere from just above freezing to nearly 100 degrees Celsius, depending on the efficiency of atmospheric heat redistribution and the thickness of the hydrogen atmosphere, which acts like a greenhouse gas, trapping infrared radiation and warming the surface. If the ocean is warm enough, you could have liquid water in contact with the atmosphere, allowing for exchange of gases and potentially supporting a biosphere similar to Earth's ocean ecosystems. If the ocean is too cold and freezes over, you'd have a layer of ice separating the liquid water from the atmosphere, but even this wouldn't necessarily preclude life because there are plenty of examples on Earth of organisms living in and under ice. And Jupiter's moon Europa and Saturn's moon Enceladus both have subsurface oceans that are considered promising targets in the search for life. The salinity of the ocean is also important. Earth's oceans have a salinity of about 3.5%, meaning 35 grams of dissolved salts per kilogram of water. And this salinity affects everything from the freezing point of water to the osmotic stress experienced by organisms living in it. We have no direct way of measuring K2-18b's ocean salinity, but we can make some educated guesses based on the planet's formation history. If the ocean formed from water ice that was delivered by comets and asteroids during the late stages of planetary formation, it would have started out relatively fresh with low salinity. Over time, the salinity would increase as water percolated through the rocky interior, dissolving minerals and carrying them to the surface. On Earth, this process has been ongoing for billions of years, gradually making the oceans saltier. On K2-18b, with its much deeper ocean and larger mass, the equilibrium salinity could be either higher or lower than Earth's, depending on the composition of the rocky interior and the rate of water-rock interactions. The presence of dimethyl sulfide actually provides a clue about the ocean's salinity, because, as I mentioned earlier, DMS production on Earth is linked to organisms dealing with osmotic stress in salty environments. If K218b's ocean is producing DMS through a similar mechanism, it suggests the ocean is indeed salty enough to create osmotic challenges for life, which in turn tells us something about the ocean's chemistry and the planet's geological history. Another factor we need to consider is the radiation environment. Red dwarfs are notorious for being active stars, prone to violent flares that can increase their brightness by factors of 10 or more in a matter of minutes, and flood nearby planets with lethal doses of ultraviolet and X-ray radiation. Young red dwarfs are especially active, experiencing frequent and powerful flares that would strip away planetary atmospheres and sterilize any life on the surface. K218, however, appears to be a relatively old and quiet star, having settled down from its youthful tantrums into a more sedate middle age. Observations show that it does experience occasional flares, but they're much less frequent and less energetic than what you'd see on a younger M-dwarf. This is crucial for habitability, because even a thick atmosphere can be eroded over time if the star is constantly bombarding it with high-energy radiation. The flares also matter for any potential surface life because ultraviolet radiation damages DNA and other biological molecules, and on Earth, organisms have evolved various strategies to protect themselves, including producing UV-absorbing pigments, developing DNA repair mechanisms, and simply hiding underground or underwater where the radiation can't reach them. On K218b, if life exists in the ocean, the water itself would provide excellent shielding against radiation. Even a few meters of water is enough to block most UV radiation, so any organisms living below the surface would be protected. Life floating at the ocean surface or in the atmosphere would have a harder time, but the thick hydrogen atmosphere might actually help by absorbing some of the UV radiation before it reaches the lower levels where organisms might be present. Planetary magnetic fields also play a role in protecting against stellar radiation. Earth's magnetic field, generated by the churning motion of molten iron in the outer core, deflects charged particles from the solar wind and prevents them from stripping away our atmosphere. Mars lost most of its atmosphere early in its history, partly because its magnetic field shut down, leaving the planet vulnerable to atmospheric erosion. For K218b, we have no direct way of measuring whether it has a magnetic field, but we can make inferences based on its internal structure. The presence of a magnetic field requires three things: a conducting fluid interior, usually molten metal, convection or motion of that fluid, and rapid rotation to generate the dynamo effect that amplifies magnetic fields. K218b likely has a metallic core that could be molten depending on the internal temperature and pressure. The question is whether it has enough internal heat to drive convection, and whether its rotation is fast enough to generate a strong magnetic field. Here's where tidal locking becomes a problem again, because tidally locked planets rotate very slowly, once per orbit, and slow rotation generally produces weak or non-existent magnetic fields. Earth rotates once every 24 hours, which is one of the reasons our magnetic field is so strong. K218b rotates once every 33 days, which is much slower and might not be enough to sustain a dynamo. However, there's a potential loophole. Even if the planet is tidally locked, its core might not be, because the core is decoupled from the outer layers by the liquid ocean and the high-pressure ice mantle. The core could be rotating faster than the surface, driven by thermal convection and tidal forces from the star, and this differential rotation could generate a magnetic field even if the surface is tidally locked. It's a speculative idea, but it's supported by some models of planetary interiors for water worlds. Then there's the question of atmospheric composition beyond just the major components. We know K2-18b has water vapor, methane, carbon dioxide, and probably DMS. But what else is lurking in that atmosphere? On Earth, the atmosphere contains nitrogen as the dominant gas, making up 78% of the total, followed by oxygen at 21%, with argon, carbon dioxide, and trace amounts of dozens of other gases making up the remaining 1%. The presence of nitrogen is crucial for life on Earth, because nitrogen is an essential component of amino acids and nucleotides, the building blocks of proteins and DNA. Nitrogen fixation, the process of converting inert atmospheric nitrogen into biologically useful compounds, is carried out by specialized bacteria and is one of the fundamental processes supporting the entire biosphere. For K2-18b, we don't yet have a detection of nitrogen or any of the noble gases like argon, neon, or helium. This is partly because these gases don't have strong spectral features in the infrared wavelengths where JWST is most sensitive, making them difficult to detect. But nitrogen and argon can be detected at other wavelengths, and future observations might be able to constrain their abundances. The presence or absence of nitrogen would tell us a lot about the planet's formation history and its potential for supporting complex biochemistry. There's also the question of clouds and hazes, which can have a huge impact on a planet's climate and habitability. On Earth, clouds reflect about 30% of incoming sunlight back to space, helping to cool the planet, but they also trap infrared radiation, contributing to the greenhouse effect. The balance between these two effects determines whether clouds have a net cooling or warming effect, and it's one of the biggest uncertainties in climate models. On K2-18b, the situation is even more complicated because we're dealing with a hydrogen-rich atmosphere that might form very different types of clouds than what we see on Earth. Water clouds are definitely possible, condensing in the cooler upper atmosphere, but you might also get clouds made of methane ice, ammonia ice, or even more exotic materials like ammonium hydrosulfide, which is common on Jupiter and Saturn. Photochemical hazes are another possibility. These are layers of tiny particles suspended in the atmosphere, created when ultraviolet light breaks apart molecules like methane, and the fragments recombine into complex organic compounds called tholins. Saturn's moon Titan has a thick photochemical haze that gives it its orange color and plays a major role in the moon's climate and chemistry. If K2-18b has a similar haze, it could affect how much starlight reaches the surface and could even provide a source of prebiotic organic molecules that rain down into the ocean, potentially feeding any life that exists there. The presence of DMS might actually tell us something about cloud formation, because on Earth, DMS plays a surprising role in climate regulation through a mechanism discovered in the 1980s. When DMS is released from the ocean into the atmosphere, it gets oxidized by hydroxyl radicals and ozone, producing sulfate aerosols, tiny particles of sulfuric acid and related compounds. These aerosols act as cloud condensation nuclei, providing surfaces on which water vapor can condense to form cloud droplets. More DMS leads to more aerosols, which leads to more clouds, which reflects more sunlight, which cools the ocean, which reduces phytoplankton productivity, which reduces DMS production, which reduces cloud formation, which warms the ocean again, completing a negative feedback loop that helps stabilize Earth's climate. This mechanism, called the sea law hypothesis after the initials of the scientists who proposed it, is still debated in terms of how strong the effect actually is, but the basic physics is sound. If something similar is happening on K2-18b, the presence of DMS could be actively regulating the planet's climate, making it more stable and more habitable than it would otherwise be. This would be a case of life not just adapting to its environment, but actively modifying it to create conditions more favorable for its own existence, which is exactly what happened on Earth when photosynthetic organisms filled the atmosphere with oxygen. When you put all of these factors together, the orbital mechanics, the tidal locking, the thick atmosphere, the deep ocean, the radiation environment, the potential for magnetic field protection, the atmospheric chemistry, the clouds and hazes, you end up with a planet that is simultaneously very different from Earth and potentially habitable in ways we're only beginning to understand. So let's talk about what kind of life could actually exist on K2-18b, because this is where astrobiology gets really fun and really speculative at the same time. The first thing we need to establish is that if life exists on this planet, it almost certainly started simple and might still be simple. When we talk about detecting biosignatures on exoplanets, we're not talking about finding evidence of technological civilizations or even complex multicellular organisms. We're talking about microbes, single-celled organisms doing the basic chemistry of life, metabolizing nutrients, reproducing, evolving. On Earth, life remained exclusively microbial for roughly 3 billion years, which is about 2/3 of the planet's entire history. Complex, multicellular life only appeared around 600 million years ago, and for most of that time it was still confined to the oceans. Life didn't successfully colonize land until about 450 million years ago, and animals with anything resembling intelligence didn't show up until much more recently. Humans, with our technology and our ability to build space telescopes and argue about the existence of aliens, have only been around for a few 100,000 years, which is a cosmic eye blink. The point is that if you were to randomly sample the history of life on Earth, the overwhelming majority of that history would show you a planet covered in microbial mats, with maybe some algae and simple animals in the oceans, but nothing you'd call intelligent. There's no particular reason to think other planets would follow a dramatically different trajectory. So when we ask what kind of life might exist on K2-18b, we should probably start with the assumption that we're talking about microbes, or at least organisms of comparable complexity. Now, what do microbes need to survive? The basic requirements are actually pretty simple. They need liquid water, which K2-18b almost certainly has. They need a source of energy, which could come from sunlight, chemical reactions, or even heat from the planet's interior. They need building block elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, often abbreviated as CNOPS, and we've already detected several of these in K2-18b's atmosphere. They need trace elements and minerals for various enzymatic and structural purposes, and they need relatively stable environmental conditions that don't swing wildly between extremes, although life on Earth has proven remarkably adaptable to harsh conditions. So, this requirement is more flexible than you might think. Let's start with energy sources. On Earth, the vast majority of life ultimately depends on photosynthesis, the process by which organisms like plants, algae, and cyanobacteria use sunlight to convert carbon dioxide and water into organic molecules and oxygen. The oxygen then supports aerobic organisms like animals and fungi that consume organic matter and breathe oxygen. Even organisms that live in environments without sunlight, like the deep sea or underground caves, usually depend on organic matter that drifted down from the surface where photosynthesis occurred, or they depend on other organisms that depend on photosynthesis, so it's photosynthesis all the way down. But there are exceptions. Some microbes practice chemosynthesis, using energy from chemical reactions rather than sunlight. The classic example is the communities of organisms that live around hydrothermal vents on the ocean floor, where superheated water rich in hydrogen sulfide and other chemicals spews out from cracks in the Earth's crust. Bacteria oxidize the hydrogen sulfide to extract energy, and other organisms eat the bacteria, creating entire ecosystems that are completely independent of sunlight. This is crucial for thinking about K2-18b, because if the planet is tidally locked with a permanent night side, any life on that hemisphere couldn't do photosynthesis in the traditional sense. It would have to rely on chemosynthesis or some other non-photosynthetic energy source. But even on the day side, photosynthesis might be tricky because the star is a red dwarf, emitting most of its energy in the infrared, rather than visible light. On Earth, photosynthesis uses pigments like chlorophyll that absorb strongly in the blue and red portions of the visible spectrum, which is where sunlight is most intense. But K2-18b receives most of its energy at longer infrared wavelengths, so any photosynthetic organisms would need to evolve pigments tuned to those wavelengths. Is this possible? Well, there are actually some Earth organisms that can do a form of photosynthesis using infrared light. Certain bacteria contain a pigment called bacteriochlorophyll that absorbs in the near-infrared, allowing them to photosynthesize in environments where visible light is scarce, like underneath layers of other photosynthetic organisms, or in deep water where visible light has been filtered out. So, infrared photosynthesis is definitely possible. It's just not the dominant strategy on Earth because visible light photosynthesis is more efficient when you have a sun-like star. On K2-18b, the situation would be reversed, and infrared photosynthesis might be the norm. There's another energy source we haven't talked about yet, and that's tidal heating. When a planet is in a slightly elliptical orbit, the gravitational pull from the star varies over the course of the orbit, causing the planet to flex and deform slightly. This flexing generates internal heat through friction, the same way bending a paperclip back and forth makes it warm. Jupiter's moon Io is the most extreme example, where tidal heating is so intense that the moon is covered in active volcanoes. Europa and Enceladus experience milder tidal heating that is thought to keep their subsurface oceans liquid despite being far from the sun. K2-18b's orbit is very close to circular, so tidal heating is probably minimal, but it's not zero. And over billions of years, even a small amount of tidal heating could contribute significantly to the planet's internal heat budget. This heat could drive hydrothermal activity on the ocean floor, creating chemical-rich environments where chemosynthetic life could thrive. Now, let's talk about the chemistry of life, because this is where things get simultaneously more concrete and more speculative. On Earth, all known life is based on carbon chemistry and uses water as a solvent. The central molecule of life is DNA, which stores genetic information, and that information is used to build proteins, which do essentially all the work of running a cell. Proteins are made of amino acids linked together in long chains, and there are 20 standard amino acids used by Earth life, though many more exist in nature. The specific sequence of amino acids determines the protein's shape and function, allowing proteins to act as enzymes that catalyze chemical reactions, structural elements that give cells their shape. molecular machines that transport materials around the cell, and countless other roles. The process of going from DNA to proteins involves an intermediate molecule called RNA, which is structurally similar to DNA but more versatile. In fact, there's a hypothesis called the RNA world hypothesis that suggests early life was based entirely on RNA, which could both store information like DNA and catalyze reactions like proteins, before DNA and proteins evolved as specialized versions of these functions. The reason I'm going through this biochemistry refresher is to emphasize how complex even the simplest life on Earth actually is. A single bacterial cell contains thousands of different types of molecules, hundreds of different proteins, complex membranes that separate the inside of the cell from the outside, energy production systems, waste management systems, reproduction machinery, and regulatory networks that control when different genes are turned on or off. And all of this has to work together in a coordinated fashion, or the cell dies. The question is whether life on K2-18b would use the same biochemical toolkit as Earth life or something completely different. The conservative assumption, and the one most astrobiologists work with, is that alien life would be broadly similar to Earth life because the laws of chemistry and physics are universal. Carbon is still the best element for building complex molecules. Water is still an excellent solvent. The same amino acids that Earth life uses would still be available and still be functional. DNA and RNA would still be effective information storage molecules, but there could be variations on the theme. Maybe K2-18b life uses a different set of amino acids, or a different genetic code, or different metabolic pathways. Maybe it uses arsenic instead of phosphorus, like that controversial study from 2010 that claimed to find bacteria that could substitute arsenic for phosphorus in their DNA, a claim that was later largely debunked but raised interesting questions about biochemical flexibility. Maybe it uses ammonia as a solvent instead of water, though this seems unlikely given that water is clearly abundant on K2-18b. The presence of dimethyl sulfide gives us a tantalizing clue about what kind of metabolism K2-18b life might have, if it exists. As I discussed earlier, DMS on Earth is produced by marine phytoplankton, specifically as a breakdown product of dimethylsulfoniopropanate, or DMSP, which the organisms use for osmoregulation and other purposes. If K2-18b life is producing DMS through a similar pathway, that tells us several things. First, it suggests the organisms are dealing with osmotic stress, which makes sense if they're living in a salty ocean. Second, it suggests they have a relatively sophisticated metabolism capable of synthesizing complex organic sulfur compounds, which requires a fair bit of biochemical machinery. Third, it suggests they might be photosynthetic, because on Earth, the organisms that produce DMS are primarily photosynthetic, though there are exceptions. But here's where we need to be careful about not being too Earth-centric in our thinking. Just because DMS on Earth comes from photosynthetic organisms doesn't mean the same has to be true on K2-18b. Evolution is endlessly creative, and if there's a biochemical niche to fill, life will find a way to fill it, often in ways that surprise us. There could be chemosynthetic organisms on K2-18b producing DMS as a byproduct of their metabolism, or organisms using DMS as a signaling molecule, or organisms that produce DMS for reasons we haven't even thought of. The important point is that DMS is a complex organic molecule that, as far as we know, requires life to produce it in significant quantities, but beyond that, we're speculating. Another consideration is the availability of nutrients beyond the basic CONOPS elements. On Earth, life needs trace amounts of various metals and minerals for different purposes. Iron is a component of hemoglobin, which carries oxygen in blood. Magnesium is at the center of chlorophyll molecules. Zinc is used in many enzymes. Cobalt is part of vitamin B12. Molybdenum is used in nitrogen fixation. The list goes on. These trace elements come from the weathering of rocks and are carried into the ocean by rivers, or they're released by hydrothermal vents on the ocean floor. On K2-18b, the deep ocean would be in contact with the high-pressure ice mantle, not directly with the rocky interior, which could limit the availability of some trace elements. However, if there are cracks or hot spots where the ice layer is thin or absent, allowing water to contact the rocky mantle underneath, you could get localized regions rich in minerals where life might concentrate. This is similar to the situation on Europa and Enceladus, where hydrothermal activity at the rock-water interface is thought to be crucial for potential habitability. Now, let's talk about timescales, because one of the most important factors in determining whether K2-18b could host life is simply how long the planet has existed in habitable conditions. On Earth, the earliest evidence for life dates back to about 3.5 to 3.8 billion years ago, only a few hundred million years after the planet cooled enough for liquid water to exist on the surface. This surprisingly rapid appearance of life has led some scientists to suggest that abiogenesis, the origin of life from non-living matter, might be relatively easy given the right conditions. But this conclusion is hotly debated because we only have one example, Earth, and it's entirely possible that Earth got lucky and life usually takes much longer to emerge, or that life on Earth actually originated elsewhere and was delivered here by meteorites, a hypothesis called panspermia. We simply don't know. The K2-18 star system is estimated to be between 2 and 4 billion years old based on stellar evolution models and measurements of the star's rotation rate and activity level. Younger stars rotate faster and are more active, so by measuring these properties and comparing them to theoretical models, astronomers can estimate the star's age, though the uncertainties are substantial. If the system is 2 billion years old, that's still a decent amount of time for life to emerge and evolve, comparable to the age of Earth when photosynthesis first evolved and started oxygenating the atmosphere. If the system is 4 billion years old, that's almost as old as our solar system, and life would have had plenty of time to not just emerge but potentially evolve into complex multicellular forms. But there's a complicating factor, which is that K2-18b might not have been in the habitable zone for its entire existence. Stars evolve over time, becoming brighter as they age, which causes the habitable zone to move outward. For a red dwarf like K2-18, the evolution is very slow, much slower than for a Sun-like star, so the habitable zone doesn't move much over billions of years. But there's another issue, which is that young red dwarfs go through a phase of extremely high activity, with frequent and powerful flares that would bombard any nearby planets with radiation and potentially strip away their atmospheres. This pre-main sequence phase can last for hundreds of millions of years, and during that time, K2-18b would have been subjected to conditions that might have been sterilizing. However, if the planet had a thick atmosphere and deep ocean to start with, it might have weathered this storm and retained enough water and atmosphere to become habitable once the star settled down. The other possibility is that K2-18b formed farther out in the solar system, where it was safer from stellar radiation, and then migrated inward to its current orbit, a process called planetary migration that's thought to be common in exoplanet systems. If this happened, K2-18b might have spent its early years as a frozen ice world before moving into the habitable zone and thawing out, at which point life could have emerged in the newly liquid ocean. We see evidence for planetary migration all over the place in exoplanet systems, including hot Jupiters that must have formed farther out and spiraled inward, so it's entirely plausible for K2-18b. Now let's address the elephant in the room, which is the question of intelligent life. Could K2-18b host not just microbes but complex organisms, maybe even a technological civilization? The honest answer is that we have absolutely no way of knowing based on current data, but we can make some educated guesses based on what we know about the evolution of intelligence on Earth. Intelligence, by which I mean the kind of complex information processing that allows for problem-solving, tool use, and abstract thinking, has evolved multiple times independently on Earth. Primates like humans and chimpanzees are intelligent. Cetaceans like dolphins and whales are intelligent. Corvids like crows and ravens are intelligent. Cephalopods like octopuses are intelligent. Elephants are intelligent. Even some insects show rudimentary problem-solving abilities. So, intelligence is not a one-time fluke. It's a strategy that evolution has discovered repeatedly because it's useful for survival in complex environments. However, technological intelligence, the kind that leads to civilization and space telescopes, and the ability to send and receive interstellar messages, has only evolved once on Earth, as far as we know. Humans are the only species that has developed agriculture, writing, mathematics, science, and technology. Why? What's special about humans that allowed us to go from hunter-gatherers to spacefaring civilization in just a few thousand years? There are many theories, but some key factors include our large brains relative to body size, our complex social structures, our ability to use language, our manual dexterity thanks to opposable thumbs, and frankly, a fair bit of luck. Many of these factors might be difficult to replicate on a water world like K2-18b. For one thing, technology requires fire, or at least it did for humans, and you can't make fire underwater. You need access to combustible materials, an oxygen-rich atmosphere, and the ability to manipulate tools with appendages like hands. A fully aquatic organism might develop intelligence but would have a much harder time developing technology. Dolphins are smart, but they're never going to build a radio telescope because they live in the ocean and don't have hands. On the other hand, maybe technology doesn't require fire. Maybe there are other pathways to civilization that don't involve metallurgy and combustion. Maybe aquatic organisms could develop biotechnology, using living organisms as tools instead of inorganic materials. Maybe they could harness geothermal energy from hydrothermal vents or tidal energy from the planet's rotation. It's hard to say because we only have one example of technological intelligence to work with, and that's us, and we're probably not typical. The Drake equation, which is a famous formula for estimating the number of communicative civilizations in the galaxy, includes a term for the fraction of life-bearing planets that develop intelligent life, and another term for the fraction of intelligent species that develop technology capable of interstellar communication. These terms are complete guesses because we have no data, but even optimistic estimates tend to put them at pretty small values, maybe 1% or 0.1% or even less. So even if K2-18b has life, the odds that its intelligent life are low, and the odds that its technological life are even lower. But here's the thing. We don't need intelligence to detect life. The biosignatures we're looking for, molecules like DMS, are produced by simple organisms just doing their thing, living and metabolizing and reproducing. If K2-18b has a thriving biosphere of microbes and maybe some simple multicellular organisms, that's more than enough to produce detectable biosignatures. And honestly, that would be just as exciting as finding intelligent aliens. Maybe even more exciting, because it would tell us that life is common in the universe and that Earth is not special. One of the biggest questions in astrobiology is whether Earth is typical or unusual. Are we living on an average planet where life emerged through ordinary processes that happen all over the galaxy? Or are we on a rare world where an improbable sequence of events led to the emergence of life, and most planets are sterile? This question has profound implications for the search for extraterrestrial life and for our understanding of our place in the cosmos. If life is common, we should find it on many planets, and the universe should be teeming with biospheres at various stages of evolution. If life is rare, we might be alone in the galaxy, or even the observable universe, and the silence we've experienced so far in our search for extraterrestrial intelligence would make sense. The detection of biosignatures on K2-18b would strongly suggest that life is common, because K2-18b is not an Earth twin. It's larger, it orbits a different type of star, it's probably tidally locked, it has a hydrogen-rich atmosphere, it's covered in a deep ocean. If life can emerge and thrive under such different conditions, that tells us that life is adaptable and that the universe has many pathways to habitability, not just the narrow Earth-like path we've been focusing on. This is why the Hycean world concept is so exciting, because it expands the definition of habitability to include a whole new class of planets that are much more common than Earth-like worlds. So, where do we go from here? Because detecting a potential biosignature on one planet is just the beginning of the story, not the end. The scientific process demands verification, replication, and multiple independent lines of evidence before we can say with confidence that we've actually found life on another world. Right now, what we have is a single set of observations from one instrument on one telescope showing spectral features consistent with dimethyl sulfide in the atmosphere of K2-18b. That's exciting, that's suggestive, that's worthy of intense follow-up investigation, but it's not proof. The next steps involve going back to K2-18b with JWST and other telescopes to gather more data, look for additional biosignatures, search for temporal variations that might indicate biological processes, and basically do everything possible to either confirm or refute the initial findings. JWST has already been allocated additional observation time for K2-18b, and as I'm recording this, those observations are being planned and scheduled. The telescope's schedule is incredibly oversubscribed, with far more proposed observations than available time. So the fact that K2-18b is getting priority access tells you how seriously the astronomical community is taking this discovery. The follow-up observations will focus on several key goals. First, confirming the DMS detection at higher signal-to-noise ratio. The initial detection was strong enough to be statistically significant, but more data will reduce the uncertainties and make it harder to explain away as instrumental noise or calibration errors. Second, looking for additional spectral features of DMS at other wavelengths. Remember that molecules have multiple absorption lines corresponding to different vibrational and rotational modes. So if DMS is really there, it should show up at multiple wavelengths in predictable patterns. Third, searching for other sulfur-containing molecules that might provide context for the DMS. For example, if we detect hydrogen sulfide or sulfur dioxide alongside DMS, that could tell us about the sulfur cycle on the planet and whether volcanic activity might be contributing to the atmospheric chemistry. Fourth, measuring the abundances of different isotopes, particularly for carbon and sulfur. Life on Earth preferentially uses lighter isotopes because they're easier to incorporate into biological molecules. So, if we see isotopic fractionation in K2-18b's atmosphere, that would be another piece of evidence pointing toward biology. Fifth, looking for seasonal or temporal variations in the atmospheric composition. On Earth, atmospheric methane shows seasonal cycles because methane-producing organisms are more active in warmer months. If K2-18b's atmosphere shows similar variations, and if those variations are correlated across different biosignature molecules, that would suggest coordinated biological activity. Of course, K2-18b doesn't have seasons in the traditional sense because it's tidally locked, but there could still be temporal variations driven by stellar activity, changes in ocean circulation patterns, or biological cycles that operate on timescales we can observe. JWST isn't the only telescope that will be studying K2-18b. Ground-based observatories are also getting into the game, and while they can't match JWST's sensitivity or spectral resolution, they can provide complementary observations at different wavelengths and with different techniques. The extremely large telescope, currently under construction in Chile, will have a mirror 39 meters in diameter, making it the largest optical telescope ever built. When it comes online in the late 2020s, it will be capable of directly imaging nearby exoplanets and characterizing their atmospheres with unprecedented detail. K2-18b is too far away and too close to its star to be directly imaged even by ELT, but the telescope will be able to observe similar planets around closer stars, providing comparison cases that will help us understand whether K2-18b is typical or unusual. The Giant Magellan Telescope and the 30-meter telescope, also under construction, will provide similar capabilities. These next-generation ground-based telescopes will revolutionize exoplanet science in the 2030s, complementing the space-based observations from JWST and future missions. Speaking of future missions, NASA is already planning the successor to JWST, a telescope concept called the Habitable Worlds Observatory, or HWO. This mission is still in the early design phase, but the goal is to build a space telescope optimized specifically for characterizing potentially habitable exoplanets and searching for biosignatures. HWO would have a larger mirror than JWST, more advanced instruments, and would operate at visible and ultraviolet wavelengths, where many important biosignature molecules have strong spectral features. The mission is currently planned for launch sometime in the 2040s, assuming funding and political will hold up, which is never a guarantee for ambitious space missions. But if HWO flies, it will be able to study planets like K2-18b in exquisite detail, potentially imaging them directly and resolving features on their surfaces or in their atmospheres. Another mission concept called LUVOIR, the Large UV Optical Infrared Surveyor, was proposed in the 2020 Astrophysics Decadal Survey, but didn't get selected for development. However, many of its design elements are being incorporated into HWO, so the basic idea lives on. LUVOIR would have been an absolute monster of a telescope, with a 15-meter segmented mirror and instruments covering ultraviolet through infrared wavelengths. It would have been capable of directly imaging Earth-sized planets in the habitable zones of nearby sun-like stars, something that's beyond the reach of any existing or planned telescope. The fact that such missions are being seriously considered and designed tells you that the astronomical community believes we're on the verge of answering one of humanity's oldest questions. Are we alone? and they're investing enormous resources into finding out. But here's the thing about interstellar distances that we need to constantly remind ourselves of. They're really, really big. K2-18b is 120 light-years away, which means the light we're observing left that planet 120 years ago, around the year 1904 here on Earth. We're seeing Ki-2-18b as it was when Theodore Roosevelt was president, when World War I hadn't happened yet, when the Wright brothers had just achieved the first powered flight a year earlier. If there are intelligent beings on K2-18b looking back at Earth with their own telescopes, they would see our planet as it was in 1904, with no radio transmissions, no artificial lights visible from space, no satellites, nothing that would indicate the presence of a technological civilization. They wouldn't know that humanity exists, or if they detected biosignatures in our atmosphere, they wouldn't know that one of those species had evolved intelligence and technology. The information barrier imposed by the speed of light is absolute and insurmountable, according to everything we know about physics. Even if we discovered unambiguous evidence of a technological civilization on K2-18b today, any message we sent would take 120 years to reach them, and their reply would take another 120 years to reach us, for a total communication time of 240 years. No one alive today would be around to hear the response. This is the fundamental problem with interstellar communication, and why MITE, messaging extraterrestrial intelligence, is such a controversial topic, as that document you provided earlier discussed in great detail. But even if two-way communication is impossible on human timescales, one-way detection is not. If K2-18b hosts a technological civilization, they might be broadcasting radio or optical signals into space, either deliberately as part of their own media efforts or inadvertently as leakage from their technology. We've been listening for such signals through SETI, the search for extraterrestrial intelligence, for over 60 years now, and we haven't heard anything yet. The famous WOW signal detected in 1977, which that document discussed extensively, remains unexplained but has never been detected again despite numerous follow-up observations. Most SETI efforts have focused on nearby sun-like stars within a few dozen light-years of Earth, and K2-18b at 120 light-years is at the edge of what current SETI surveys can detect, assuming the aliens are transmitting with power levels comparable to what we use. But there's been some discussion in the SETI community about whether we should specifically target planets where we've detected biosignatures, on the logic that life-bearing worlds are more likely to host intelligence than sterile ones. This makes sense statistically, though the probability is still vanishingly small. If K2-18b has life, maybe it's microbial, maybe it's complex multicellular organisms, or maybe, just maybe, it's a civilization that would be very interested to learn they're not alone either. The Breakthrough Listen project, funded by Russian billionaire Yuri Milner, is currently the most comprehensive SETI program in operation, and they have observed K2-18b looking for radio and optical technosignatures. As of the time I'm recording this, they haven't reported any detections, which isn't surprising because, again, the odds are astronomically low, but it's worth checking. Another Breakthrough Initiatives project called Breakthrough Starshot is even more ambitious, proposing to send tiny spacecraft to nearby star systems using laser-propelled light sails that could accelerate to 20% the speed of light. At that velocity, a probe could reach Proxima Centauri, the nearest star system, in about 20 years, and K2-18 in about 600 years. The technology doesn't exist yet, and there are enormous engineering challenges to overcome, but it's not impossible in principle. If humanity is still around and still interested in exploring the galaxy several centuries from now, we might actually send a mission to K2-18b to study it up close. Of course, by the time a probe arrived, we'd already know a lot about the planet from telescopic observations, but there's no substitute for in situ measurements. A spacecraft orbiting K2-18b could study its atmosphere in far greater detail than any telescope, potentially even descending into the atmosphere to collect samples and analyze them directly. It could search for life not just by looking at bulk atmospheric composition, but by examining individual particles, looking for cellular structures or complex organic molecules that would be impossible to detect remotely. It could study the ocean if the planet has one, either by analyzing the composition of water vapor in the atmosphere or by deploying probes that splash down and dive beneath the surface. The challenges of exploring a water world would be immense, but we're developing the technology here on Earth through missions to subsurface oceans in our own solar system, particularly Europa and Enceladus. NASA's Europa Clipper mission, launching in 2024, will fly by Europa dozens of times, studying its ice shell and subsurface ocean and looking for plumes of water vapor that might be erupting from the surface. If plumes are found, a future mission could fly through them and collect samples, analyzing them for signs of life without even needing to land on the surface. Similar strategies could be used for K2-18b, if we ever send a mission there, though the timescales involved make this firmly in the realm of science fiction for now. But let's bring things back to the present and talk about what the detection of biosignatures on K2-18b would mean for humanity, assuming it holds up under scrutiny, and we become increasingly confident that we're actually seeing evidence of life. This would be, without exaggeration, the most important scientific discovery in human history. It would fundamentally change our understanding of our place in the universe and would have profound philosophical, religious, and cultural implications. For scientists, it would answer the question of whether Earth is unique and would provide a second data point for understanding how life emerges and evolves. Right now, we have a sample size of 1, which makes it impossible to distinguish between universal principles and local accidents. Does all life use DNA, or is that just what happened on Earth? Does all life require liquid water, or are there organisms that use other solvents? Does the evolution of intelligence require specific environmental pressures, or is it an inevitable outcome given enough time? We can speculate about these questions, but we can't answer them without finding actual alien life to study. A second independent origin of life would let us start comparing and contrasting, looking for commonalities and differences, and building a general theory of biology that goes beyond just Earth biology. For the general public, the reaction would probably be a mix of excitement, fear, curiosity, and indifference, depending on personal beliefs and values. Some people would see it as confirmation that we're not alone and would find comfort or inspiration in knowing that life is common in the universe. Others would see it as threatening or disturbing, either because it challenges religious beliefs about humanity's special place in creation or because it raises fears about hostile aliens, even though life on a planet 120 light-years away poses exactly zero threat to us. Still others would be fascinated by the scientific details and would want to know everything about this alien biosphere, what the organisms look like, how they metabolize, whether they're related to Earth life in any way. And some people honestly wouldn't care that much, which is fine. Not everyone has to be interested in astrobiology. The religious responses would be particularly interesting to watch because different faith traditions would interpret the discovery in different ways. Some religious leaders have already stated that the existence of alien life would not contradict their theological beliefs. The Vatican, for example, has said that discovering aliens would not challenge Catholic doctrine because God could have created life on other worlds just as He created life on Earth. Other religious traditions might have more difficulty reconciling alien life with their teachings, particularly those that place humanity at the center of divine creation. But I suspect that most religious people would find ways to incorporate the discovery into their existing worldviews, just as they have done with previous scientific discoveries that initially seemed threatening to faith, like heliocentrism and evolution. The philosophical implications are perhaps even deeper than the religious ones. If life exists on K218b, that means the universe is not sterile and meaningless. It's a place where matter organizes itself into complex structures, capable of metabolism, reproduction, and evolution. The fact that this happened independently at least twice suggests that it's a natural outcome of the laws of physics and chemistry, not a miraculous fluke. This has implications for questions about the nature of life, consciousness, purpose, and meaning. Are we just chemical reactions, or is there something more? If life emerges naturally wherever conditions permit, does that make it more or less special? These are questions that philosophers and theologians will be debating for centuries. There's also the practical question of what we should do with this information. If we're confident that K218b has life, should we try to communicate with it, even though any response would take centuries? Should we prioritize learning more about this world, or should we search for life on other planets to see how common it really is? Should we protect K218b from future interference, establishing it as a kind of cosmic nature preserve, or should we view it as a potential target for future exploration and maybe even colonization? Though the latter seems highly unlikely given the distances involved and the fact that K218b probably isn't very hospitable to human life. These questions don't have easy answers, and they'll require international cooperation and consensus to address, which historically has been challenging when it comes to space exploration and planetary protection. The Outer Space Treaty of 1967 establishes some basic principles for the exploration and use of outer space, including the idea that celestial bodies should be preserved for peaceful purposes, and that we should avoid harmful contamination. But the treaty was written when we didn't know if exoplanets existed, let alone whether they might harbor life. We'll need updated international agreements to deal with the realities of a universe where life-bearing planets are within our reach, at least telescopically. But I'm getting ahead of myself because we need to remember that we don't yet have definitive proof of life on K218b. What we have is a detection of dimethyl sulfide that's best explained by biological processes given our current understanding, but our understanding is incomplete, and there's always the possibility that follow-up observations will reveal a mundane explanation. Maybe there's some exotic photochemistry we didn't think of. Maybe there's a geological process unique to water worlds that produces organic sulfur compounds. Maybe the detection is spurious, the result of instrumental artifacts or data reduction errors that will be caught when the observations are peer-reviewed and independently analyzed. This has happened before, most notably with the phosphine on Venus claim that I mentioned earlier, which went from "we found alien life" to "we maybe found phosphine but probably didn't, and even if we did, it's probably not biological" in the space of a few months. Science is a self-correcting process, and that's a feature, not a bug, but it does mean we need to maintain healthy skepticism even when the results are exciting. The peer review process for the K2-18b findings is ongoing, with multiple teams independently analyzing the JWST data to see if they reach the same conclusions. Some preliminary results from these independent analyses have been presented at conferences, and the consensus seems to be that, yes, there's definitely something interesting in the spectrum, and yes, DMS is a plausible explanation, but more data is needed. The scientific method is slow and methodical by design, and that's frustrating when you just want to know if we found aliens or not, but it's the only reliable way we have of distinguishing true discoveries from false alarms. One thing that gives me optimism about the K2-18b detection is that the team who made the discovery has been appropriately cautious in their claims. They're not saying, "We found life," they're saying, "We found a molecule that we can't explain without life, but we acknowledge the possibility of alternative explanations and we're calling for follow-up observations to test the hypothesis." This is exactly the right approach, and it's very different from some previous biosignature claims that were presented with more confidence than the data warranted. The team is also being transparent about their methods and data, making everything available for independent verification, which is crucial for building trust in the results. Another encouraging sign is that the detection is based on multiple spectral features, not just a single line, and those features are consistent with each other and with laboratory measurements of DMS under various conditions. This makes it harder to explain away as instrumental noise or some unknown contaminant. But ultimately, we won't know for sure until we get more data, and that's going to take time. JWST can only observe K2-18b when the planet is transiting its star, which happens once every 33 days, and each transit provides only a few hours of usable data. To build up a high-quality spectrum with low noise, you need to observe multiple transits, and with JWST's busy schedule, that means observations will be spread out over months or even years. So we're in for a long wait before we have definitive answers. But that's okay, because this is how science works. Slowly, carefully, building up evidence piece by piece until the picture becomes clear. In the meantime, the search for life will continue on other fronts. JWSI is observing dozens of other potentially habitable exoplanets, looking for biosignatures in their atmospheres. Some of these planets orbit closer stars and might be easier to study in detail. The TRAPPIST-1 system, for example, has 7 Earth-sized planets orbiting a red dwarf just 40 light-years away, and several of those planets are in the habitable zone. JWST has already begun observing them, though initial results suggest that at least some of the planets may not have substantial atmospheres, possibly because they were stripped away by stellar radiation when the star was younger. Other promising targets include Proxima Centauri b, the nearest exoplanet to Earth at just over 4 light-years away, and LHS 1140b, a super-Earth orbiting a red dwarf 40 light-years away that might be a water world similar to K2-18b. Closer to home, we're also searching for life within our own solar system, and some of the most promising targets are right here in our cosmic backyard. Mars once had liquid water on its surface and might still have subsurface aquifers where microbial life could persist. Europa and Enceladus have subsurface oceans that are considered among the most likely places in the solar system to find life. Titan has lakes and seas of liquid methane and ethane, and a complex organic chemistry that some scientists think could support exotic forms of life. Venus, despite its hellish surface conditions, has a layer of clouds at an altitude where temperatures and pressures are Earth-like, and some researchers have speculated that microbial life could exist floating in those clouds, though this is controversial and the phosphine detection didn't help. If we find life anywhere in the solar system, even if it's just microbes in Martian soil or Europa's ocean, that would be almost as significant as finding life on an exoplanet, because it would tell us that life arose multiple times in the same stellar system, which would strongly suggest that life is common throughout the universe. On the other hand, if we explore all these worlds and find nothing, that would also be informative, suggesting that life is rarer than we hoped, and that Earth might be unusual after all. The Fermi paradox, which asks why we haven't detected any signs of alien civilizations if the universe is so big and so old, might have a simple answer. Life is hard, and intelligence is even harder. But I don't think that's the case, and the detection of potential biosignatures on K218b gives me hope that we're living in a universe teeming with life, even if most of it is microbial and we're unlikely to ever communicate with it. There's something profoundly humbling about the realization that Earth is not the center of the universe, that our sun is just one star among hundreds of billions in our galaxy, that our galaxy is just one among trillions in the observable universe, and that life, if it exists on K218b, is not unique to our little blue marble, but is a cosmic phenomenon occurring wherever conditions permit. This perspective, sometimes called the cosmic perspective, has a way of putting human concerns into context and reminding us that we're all part of something much larger than ourselves. At the same time, it makes our existence feel even more precious and remarkable, because even if life is common, the specific history that led to us, to human consciousness and civilization and art and science, is probably unique and will never be repeated. We are, each of us, the products of billions of years of cosmic and biological evolution made of atoms forged in the cores of dying stars, animated by chemical reactions that somehow give rise to thoughts and feelings and the ability to wonder about our place in the universe. And now, for the first time in human history, we might be on the verge of discovering that this miracle of complexity and consciousness has occurred elsewhere, that we're not alone, that the universe is filled with other stories of emergence and evolution, even if those stories are very different from our own. That's why the detection of dimethyl sulfide on K218b matters, not just as a scientific curiosity, but as a potential turning point in human history. The moment when we stopped wondering if life exists elsewhere and started studying it, learning from it, trying to understand how it fits into the broader picture of cosmic evolution.